Quantum entanglement is one of the most mysterious and powerful phenomena in physics. Once dismissed by Einstein as spooky action at a distance, it's now at the heart of revolutionary breakthroughs, from ultra-secure communication to the future of deep space exploration. What once seemed like science fiction is quickly becoming science fact. Entangled particles can remain connected across thousands of kilometers. Quantum teleportation has already been demonstrated between satellites and Earth, and researchers are now building the foundation for a quantum internet that may one day link planets, probes, and people in real time. In this documentary, we'll explore the science behind entanglement, the experiments that proved it, its role in today's quantum technologies, and how quantum teleportation could transform the future of space travel, communication, and beyond. Quantum entanglement is one of the strangest and most fascinating phenomena in all of science. So much so that even Albert Einstein once called it spooky action at a distance. Yet today, it's no longer just a theoretical oddity. Entanglement has been confirmed in countless experiments and is now paving the way for next-generation technologies, from quantum computers to secure communication systems. At its core, quantum entanglement is a type of connection between particles that defies our everyday understanding of physics. When two particles, such as photons or electrons, become entangled, they don't just behave like two separate objects. Instead, they form a single system, no matter how far apart they are. Measuring one particle instantly gives you information about the other, not because they send messages back and forth, but because they exist in a unified quantum state. A useful metaphor is that of a dance duet. You can't fully describe the performance by observing just one dancer. The choreography emerges from their synchronized motion. Similarly, entanglement is an emergent property. It's not about the individual particles alone, but the correlations between them. In many experiments, scientists start with a single particle and use special techniques, like sending it through a nonlinear crystal to split it into two entangled particles. These are then separated by large distances. Before measurement, each particle is in a state of superposition, simultaneously existing in multiple states, such as spinning both up and down. But once one particle is measured, the state of the other becomes defined instantly, regardless of the distance. This isn't a violation of the speed of light. While it may seem like information travels instantly, what actually happens is that the outcome of each measurement is random, and randomness can't be used to transmit information. So you can't use entanglement to send messages faster than light. Still, the connection between the particles remains. As Caltech's Thomas Vitek puts it, there can be correlation without communication. The particles act as if they're parts of the same object, even when they're worlds apart. Even more astonishingly, entanglement doesn't stop with pairs. Physicists now study systems involving hundreds, thousands, or even millions of entangled particles. These large systems exhibit collective behavior, like flocks of birds turning in unison. Many believe these collective quantum states could help simulate complex systems and reveal new physics. Entanglement is also becoming the backbone of next-generation quantum technologies, laying the groundwork for things like ultra-secure communications, precision sensors, and futuristic space-based networks. Before quantum entanglement became a foundational concept in modern physics, it was the center of a heated philosophical debate, and one of its most vocal critics was Albert Einstein. By the 1930s, Einstein had revolutionized our understanding of space and time with his theory of relativity. Yet he was uneasy about the rise of quantum mechanics. The idea that particles didn't have definite properties until they were observed felt deeply unsettling to him. In his view, the universe should be local and deterministic, meaning that objects have real, fixed states and that no influence can travel faster than the speed of light. Quantum mechanics, however, suggested otherwise. It introduced the concept of superposition, where particles could exist in multiple states simultaneously, and entanglement, where particles remained mysteriously linked even across vast distances. Einstein, along with physicists Boris Podolsky and Nathan Rosen, challenged these ideas in a 1935 paper now known as the EPR paradox. They proposed a thought experiment involving two particles that had once interacted and then moved far apart. According to quantum theory, measuring one particle would immediately determine the state of the other. To Einstein, this implied either that information was traveling faster than light, violating relativity, or that the act of measurement itself was changing reality, which he found equally unacceptable. He offered a third option: maybe quantum mechanics was incomplete. Perhaps each particle carried hidden variables, unknown pieces of information that predetermined their outcomes. If those variables existed, then the spooky correlations of entanglement could be explained by classical physics. This local hidden variable theory appealed to Einstein's sense of order and causality. But at the time, it was just a philosophical argument. There was no way to test whether quantum mechanics or hidden variables were right. Obviously, quantum entanglement remained a philosophical puzzle for decades, provocative, yet experimentally unverified. That changed in 1964, when physicist John Bell introduced a landmark concept, Bell's theorem. It showed that if so-called hidden variables existed, unseen factors that Einstein believed might explain entanglement, then certain statistical correlations between entangled particles would be constrained. These limits became known as Bell inequalities. Quantum mechanics, however, predicted that these inequalities would be violated under specific conditions. That set the stage for real-world experiments to determine whether reality behaves according to classical intuition or quantum theory. The first significant test came in the early 1970s, when John Clauser and Stuart Friedman measured correlations between entangled photons. Their results supported quantum predictions, but left room for doubt due to experimental inefficiencies. The turning point came in the 1980s with Alain Aspect and his team in France. In a series of groundbreaking experiments, they used rapid switching polarizers and time-sensitive detection methods to eliminate key loopholes in earlier tests. In one experiment, they changed the measurement settings while the photons were already in flight, ensuring no signal could influence both outcomes. The violations of Bell's inequalities were decisive, ruling out local hidden variable theories. This was more than experimental confirmation. It was a profound blow to classical realism. Entanglement was no longer an abstract idea. It was real, observable, and measurable. Fast forward to 2015, 3 independent experiments in the Netherlands, United States, and Austria achieved what physicists had long awaited: loophole-free Bell tests. With high-efficiency detectors and strictly enforced locality constraints, these experiments confirmed the predictions of quantum mechanics without the assumptions earlier tests had to make. These advancements established entanglement as a tool, not just a test. Today, researchers entangle a wide array of systems: photons, electrons, ions, atoms, and even micromechanical oscillators. They use entanglement in quantum computing, communications, and fundamental physics experiments. While the technical methods behind entanglement generation vary, the implications are clear. We now have robust, repeatable ways to create and verify entangled systems. And in recognition of this progress, the 2022 Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their pioneering work, cementing entanglement as a cornerstone of modern science. Quantum entanglement doesn't just happen in controlled lab experiments, it's part of the natural world. For example, when atoms in a star transition from high-energy states, they may emit pairs of entangled photons. These interactions occur constantly in the Sun and other stars, making entanglement a byproduct of the universe's most fundamental processes. In condensed matter systems, entangled states naturally arise in quantum magnets, superconductors, and topological materials. In these environments, the spins of countless electrons can become intertwined across large regions of a solid. This gives rise to many-body entanglement, where hundreds or thousands of particles behave not as individuals, but as a coherent whole. Entanglement is also becoming a subject of study in quantum biology. Some researchers suggest that birds may navigate using entangled electrons in their visual systems. Others explore whether quantum coherence, a phenomenon related to entanglement, plays a role in the high efficiency of photosynthesis. While speculative, these theories are pushing entanglement into the realm of living systems. In today's labs, the focus has shifted from proving entanglement to using it. Quantum physicists are refining how to control, stabilize, and scale entangled systems. Experiments often take place in ultra-high vacuum and at cryogenic temperatures, where quantum systems are isolated from environmental noise that causes decoherence. Modern research platforms now feature photonic circuits, ion arrays, and programmable cold atom lattices. These are used not just to test theory, but to build functional systems for quantum computing and sensing. For example, quantum simulators entangle many particles to model systems that would overwhelm classical supercomputers, such as high-temperature superconductors or strongly correlated electron fluids. Entanglement is also a driving force in quantum phase transitions between different quantum states of matter governed by entanglement rather than thermal energy. Studying how entanglement spreads or collapses helps physicists understand the boundaries between exotic states of matter. Another cutting-edge application is quantum sensing. Entangled particles can enhance measurement sensitivity far beyond classical limits. Research teams are now building sensors that use entanglement to detect gravitational shifts, magnetic anomalies, and even possible signatures of dark matter. One vital concept is entanglement entropy, which quantifies the amount of entanglement in a system. This tool connects quantum mechanics with information theory and thermodynamics, offering insight into how quantum systems store and transmit information. Despite its power, entanglement is fragile. Tiny interactions with heat, light, or motion can destroy it. That's why protecting entangled systems, through topological encoding, dynamic feedback, or error correction, is one of the highest priorities in experimental design. An essential method enabling future quantum networks is entanglement swapping, where two particles that have never interacted directly become entangled through a third, intermediary system. This technique underpins the development of quantum repeaters, devices that will eventually allow entanglement to stretch across continents, oceans, and deep space. Entanglement instantaneous correlations have the potential to revolutionize secure communication, synchronization, and coordination across vast distances. A key milestone was China's 2016 launch of the MISSIA satellite, the world's first quantum communication satellite. It transmitted entangled photons from orbit to ground stations over 1,200 kilometers apart. Despite the challenges of atmospheric interference and long-distance transmission, the entangled states remained intact. This proved that entanglement can survive the harsh conditions of space. One of the most promising applications of entanglement in space is quantum key distribution, QKD. It enables unbreakable encryption. Any interception attempt disturbs the entangled state, revealing the breach. Unlike classical systems, which require fiber optics or signal boosters, satellite-based quantum links offer a scalable global solution for secure data. Entanglement could also enable highly accurate timekeeping and navigation. With entangled systems on Earth and in orbit, we can synchronize clocks and calibrate sensors with exceptional precision. This is essential for deep space missions and autonomous robotic explorers, where real-time synchronization is crucial, even if information cannot travel faster than light. Countries around the world are building ground-based and satellite-supported quantum networks. These infrastructures aim to extend entanglement beyond national boundaries and into space, potentially enabling a future quantum internet. Through entanglement swapping, multi-hop connections between satellites and Earth stations could form the backbone of global quantum communication. Entangled quantum sensors may also help detect gravitational waves or dark matter, using subtle shifts in quantum correlations to spot tiny changes in space-time. However, the biggest hurdles are environmental noise, photon loss, and the fragility of entangled particles. Addressing these issues requires better photon sources, error correction techniques, and space-hardened components. Interplanetary communication is limited by the speed of light. Messages between Earth and Mars, for instance, can take up to 22 minutes one way. For spacecraft farther out, delays stretch into hours. While entanglement won't let us bypass this limit for transmitting classical data, it opens a new framework for secure verification, synchronization, and coordination. Quantum teleportation is central to this approach. It enables the transfer of a quantum state across space without physically sending the particle itself. The process relies on three elements: a shared entangled pair, a local quantum measurement, and the transmission of classical data. Once the data arrives, the receiver reconstructs the original quantum state. Teleportation has already been demonstrated over fiber and via the MISHA satellite. These experiments show that quantum information can be shared between distant systems, a vital capability for synchronizing quantum processors or verifying data in space missions. For example, a spacecraft heading to Saturn could use entangled links to validate operations or confirm secure commands from Earth. Quantum synchronization is another key benefit. Entangled systems can maintain shared timing, boosting the accuracy of space-based navigation systems. Distributed quantum computing may also become viable, with processors on Earth and in space working together as a single logical system. However, entanglement is fragile. In deep space, cosmic radiation, extreme temperatures, and mechanical disturbances can degrade quantum links. Photon loss is another issue, especially over long distances. Quantum repeaters, designed to relay and rebuild entangled connections, will be essential, stationed on satellites, planetary relays, or Lagrange points. Power constraints and equipment bulk also limit current deployment. Quantum communication hardware still requires lasers, detectors, and cooling systems. Miniaturizing and optimizing these technologies is a key area of active research. Hybrid networks are emerging as a near-term solution. In these setups, classical systems manage basic communication, while quantum channels handle security, authentication, and critical synchronization. As hardware improves, these networks could evolve into fully quantum systems supporting complex, space-based architectures. Ultimately, entanglement won't replace classical signals, but it will redefine coordination in space missions, ensuring trust, integrity, and precision across interplanetary distances. A 2024 experiment led by Professor Prem Kumar at Northwestern University successfully demonstrated quantum teleportation over 30 kilometers of standard fiber optic cable already carrying internet traffic. By isolating a stable wavelength and filtering out noise, the team enabled fragile quantum signals to coexist with conventional data. This proves that quantum protocols can operate on existing infrastructure, including optical laser links in space. Teleportation involves 3 steps: sharing an entangled pair, performing a quantum measurement, and using classical data to reconstruct the original state. In orbit, this has been tested via the Mycius satellite. Future missions will attempt longer distance teleportation and the use of entanglement swapping to enable interplanetary quantum repeaters. The same principle applies to modular quantum computing. Researchers at the University of Oxford have already linked 2 separate quantum processors using teleportation. Their experiment showed that logical operations could be executed across distant systems using photonic entanglement, a model ideal for space computing, where modules may be distributed across platforms. This architecture supports a quantum internet for space, one that enables encrypted communication, distributed quantum memory, and system-wide coordination. A Mars base, for instance, could remain synchronized with Earth through teleportation-based links. Probes could securely relay data, and networked systems could self-correct in the event of damage. Quantum teleportation also provides system redundancy. If one module fails, information can be rerouted and rebuilt elsewhere in the network. This is critical in deep space, where hardware replacements are impractical, though challenges like signal loss, environmental interference, and hardware complexity remain. Progress is steady. Field tests are expanding, and 2025 marks a global push toward quantum infrastructure. In the future, teleportation will be the connective tissue of a space-based quantum network, one defined not by distance, but by shared quantum logic. As exploration expands, teleportation won't just support communication. It will redefine how we build, coordinate, and connect across the cosmos. Now we've explored how particles can remain connected across vast distances, enabling technologies like quantum key distribution, ultra-secure communication, and even quantum teleportation. From Bell's early tests to satellite-based quantum links, experiments have confirmed that entanglement is both real and reliable. In both the lab and nature, entangled systems are now powering quantum computers, precision sensors, and complex simulations. Teleportation, built on entanglement, is already transferring quantum information between Earth and orbit. In the future, it could support synchronized, secure networks across space, linking ground stations, satellites, and even interplanetary missions. From foundational science to space-age innovation, entanglement is no longer just a mystery. It's becoming a vital part of the future of communication, computing, and exploration. Thank you for watching. If you enjoyed this documentary, don't forget to like, share, and subscribe for more deep dives into the world of quantum science and space.